So with that, let's begin the session. And we have Veronika Hubey from UC Davis telling us about entanglement relations and bulk locality.
Thank you very much. It's a pleasure to be back here. I was here at the opening ceremony and it has really blossomed since then. So I'm very delighted to help you celebrate 20th anniversary of ADS-CFT, which pretty much spans my academic career. I got hooked on it the moment it came out and haven't yet gotten over my fascination with it. Still working on it. So this will be about sort of entanglement relations in ADS-CFT and what they tell us about locality, which is very much a work in progress, just as a disclaimer. So at 20 years, ADS-CFT has been, of course, extremely useful in many directions. Maybe the most obvious one is sort of in the direction where one uses the gravitational system to learn about various systems that are akin to the ones that we have around us in nature, that are sort of strongly coupled field theories. So this has been an invaluable tool to sort of gain insight into these systems. But at the same time, there is a great potentiality of learning using the field theory, which doesn't have manifest gravity, to learn about quantum gravity, okay, because it's a precise correspondence. And this direction is only sort of beginning to be mined. So I think ADS-CFT, we have only seen the sort of tip of the iceberg of its utility. But of course, to make this really work, we have to really understand the dictionary sufficiently well. And so things that we want to learn and we're curious about from the very start are things like, how does this bulk dynamical geometry emerge from the dual CFT? And for example, what CFT quantities would describe the bulk metric? More importantly, what about the dynamics? What encodes the bulk dynamics? And even more ambitiously, if you have, for example, local operator in the bulk, how do you describe that in the CFT? Those sorts of questions have arisen with various new insights over the last few years. And so this is very much sort of active area of investigation. One could ask, if you have, say, not access to the full CFT, but just some subset of it. Suppose you don't know the Hamiltonian, you don't know the dynamics, but you're given a state of the CFT at some instant in time. Is there any sensible bulk description of that? What would be the bulk region, for example, that would encode? Or conversely, if you are given the dynamics, but you're only given some subregion of the CFT, then is there a natural bulk region that this CFT subregion would correspond to? Okay, this is something that some people have called subregion duality. Even more interestingly, one would like to learn, what happens in the extreme regimes where the bulk space-time manifestly breaks down, like inside black holes near curvature singularities, or maybe even further out near the horizon. And since the CFT provides a full, complete description, one wants to understand, well, how does that manifest itself in the bulk? What replaces the classical GR and resolves these singularities? And the recent hints over the last few years have been that entanglement plays a crucial role in gaining insight to these questions. And so as Tadashi very nicely reviewed for us, so I don't have to sort of remind you, the entanglement entropy is the measure, a very useful measure of entanglement. I am not going to focus on Renyi entropies, the higher Renyi entropies, but solely on entanglement entropy, which you can think of as the von Neumann entropy of a reduced density matrix for a system when you trace out its complement. And in just for ease of notation, I'll sometimes be using the subscript to denote a subsystem, and sometimes these are equivalent. Okay, so this entanglement entropy has lots of interesting relations if you have multiple, if you separate the system into not just a bipartition, but into more partitions. And so I'll give you a few of these interesting relations. So this will be probably the most busy slide, to warn you. So the most basic one, in some sense, is the so-called subadditivity, where if you have two systems, A and B, not necessarily with AB being in a pure state, AB can be in some mixed state. So think of partitioning in three parts, A, B, and the complement. Then the sum of the individual entanglement entropies must always exceed the combined entanglement entropy. And a useful way to represent this is as a positivity of the so-called mutual information, which is defined simply as the difference between these two, and measures sort of the amount of correlation between the subsystem A and B. And so, since the amount of correlation can't be negative, that automatically shows you that the mutual information can't be negative. A more stringent inequality is the so-called strong subadditivity, where if you have a partition into, well, you have systems A, B, and C, then this is the relation of strong subadditivity. The combined system for A and B has plus a combined system for B and C. Those entanglement entropies have to exceed these two. And you can express that as a positivity of conditional mutual information, which is defined as taking the mutual information between the system A and the combined system BC, and then subtracting off just the one with the system B. And so the statement tells us that this amount of correlation, this mutual information, is monotonically increasing under inclusion, which makes perfect sense. If you have two systems that have some amount of correlation and you enlarge one of them, well, certainly the correlation can't decrease. Another interesting relation is the so-called monogamy of mutual information, which again, in terms of this type of notation, is expressed as this relation. And it can be rewritten as negativity of a so-called tripartite information, where you take, which you can rewrite as the correlation between A and B plus the correlation between A and C minus the correlation between A and BC. And so you see that here, what this negativity would tell us is that, well, this captures the deviation from extensivity. And so if this quantity is negative, that means that the correlation between A and the combined system B and C is actually greater than the correlation between A and B and between B and C. And so it's superadditivity of mutual information. Okay? And while the first two, subadditivity and strong subadditivity, are in fact true inequalities for any quantum state, the monogamy of mutual information does not hold universally for any quantum state. It holds for special classes of quantum states. So this will be, this quantity, this monogamy of mutual information will be the sort of star of the show. And so I'll tell you a little bit more about the insights we've gained from looking at this relation, in particular in hologram. Okay, so although monogamy of mutual information need not hold for generic quantum system, it does hold whenever that correlation is purely quantum by sort of monogamy of entanglement. So if you have a correlation between A and B, let's say, monogamy tells you that that correlation cannot be shared by some other system C, and therefore if you, the sum of A, the correlation between A and B and A and C has to be smaller than the correlation between A and the combined system. Okay. So anytime you have the mutual information composed of quantum entanglement, then this MMI, this monogamy of mutual information, is satisfied. The tripartite information is negative. Now, that sort of, this monogamy idea makes it rather tempting to associate capture this mutual information by something that only knows about those two subsystems and cannot be shared by a third party. So that's very natural to think of it fancifully as maybe a thread connecting the subsystem A and the subsystem B. And of course, that because the thread has only two ends, that automatically implements monogamy. Now, you might think that, okay, that this then doesn't really allow us to capture the classical correlations, but in fact, I think that's not, that's too fast. If you indulge me in sort of fanciful speculation, I would say that, in fact, it does naturally, that notion would naturally lend itself to also capturing the classical correlations, because after all, for systems that are described by some effective classical description in nature are fundamentally quantum mechanical. And so this might be related, might be a similar picture as I and Max Gautam wrote last month in sort of trying to postulate, conjecture how you might think of emergence of classicality from quantum mechanics in terms of something that we dubbed microequilibration. In any case, I'll sort of try to see where this intuition of, or the picture of thinking of this monogamous entanglement that is captured by some thread leads us. And in fact, it will give us insights into holography. So it turns out that, as had already been proven quite a few years ago, that monogamy of mutual information is satisfied for any CFT which has a holographic dual for the states that have geometrical representation in terms of classical bulk geometry. And so, in some sense, you might view this as a lesson that even though we have classical correlations, the quantum part of the entanglement dominates over this classical part, which could have allowed positivity of tripartite information and therefore violation of this MMI. And you might think that that's somehow at odds with the bulk geometry being classical, it's a Larchen theory, but in fact we know that that classical bulk really has genuinely quantum features, because after all, the entanglement entropy for a bipartition of a pure state is still non-zero, whereas classically, if you had zero total entropy, you could never get non-zero entropy of the subparts for this classical system. Okay, so this idea. As long as they have a geometrical dual.
Okay.
So all of the talk will be in the regime of large n and large lambda, where we have a classical bulk geometry. And for any such, so that certainly is fine for high excitations. Typical such thing will be described by a bulk black hole. And yes, for all such things, monogamy of mutual information holds.
Nice.
So you might then speculate that in this picture, these conceptual threads in a pictorial language might sort of be the thing that sort of weaves together the fabric of bulk space-time. And in fact, similar types of ideas have already been around for a while. The idea that geometry sort of emerges from entanglement, and one's famous ER is EPR conjecture, and in some sense, the sort of whole idea of tensor networks also is very reminiscent of this monogamy thread-like interpretation. Okay, so with that prelude, let me tell you what motivates this particular exploration that I'll dive in. And again, the broad motivation is just elucidating holography, understanding what sort of structure, entanglement structure would characterize CFD states that have a gravity dual, and what is the precise relation of this bulk spacetime to entanglement, and how in fact does entanglement build up geometry. And we have come to appreciate very much that bulk geometry, in fact, geometrizes these entanglement relations very, very nicely. And so this subadditivity, strong subadditivity, mutual monogamy of mutual information, all these are very easy to prove with the geometrical description, so I'll show you in a moment. But at the same time, this geometrical description seems to simultaneously obscure the differences between these relations, in particular because the proof looks very similar for both these universal quantities relations as well as the non-universal one. It hides that difference between them. And so I want to ask, why is it that according to this geometrical holographic entanglement entropy, these look the same? Why is it that they seem to be fundamentally different? And so understanding this distinction then would give us a bit more insight into sort of the essence of how does the bulk emerge from this entanglement. Okay, so the preview is sort of, I asked this question, why do these look the same? And in fact, they look the same only at the leading large N description. If you take subleading corrections, you do see a difference between them. But I want to point out that, well, in fact, well, and just to say why they're identical at this leading order, we'll see this in a moment. But the essential feature is that you sort of cancel surfaces. Okay, this will sound very obscure until the next few slides where I explain what I mean. But what one wants to see whether there's a distinction already, even at this leading order in N, the pure geometrical level, whether there's already a distinction between these, even though in the sort of canonical geometrization they do look the same. Okay, and so the hint will come from a recasting of this geometrical description in terms of something that Hedrick and Friedman called bit threads, which I'll also review, where the strong subadditivity was trivial, but monogamy of mutual information is much harder to prove. And in fact, in literature so far, there has not been any proof, although Matt Hedrick and company are constructing a proof, and I'll show you a geometrical proof of this relation. Okay. And in fact, it follows from assumption that there exists something that Matt calls cooperative flows. And so this question translates to what guarantees the existence of such cooperative flows. And my answer to this is that it's really deeply connected to bulk locality. Okay, so unlike SSA, which doesn't really hinge on bulk locality, but it doesn't hinge on bulk locality to the same extent as monogamy of mutual information. Okay, yeah.
So if in some system you calculate that the MMI doesn't hold, then is it sufficient to conclude that it won't have a bulk?
Yes, indeed.
It is sufficient.
Indeed. And that's one of the one of the motivational features for people to study this. You might, there's also higher tower of entanglement relations. People sort of explore this in the context of the so-called entropy code. And indeed, there's only a subset of them that does hold that's guaranteed to hold geometrically, but not guaranteed to hold generically. And so one might hope that knowing the set of all of these will then provide the sort of criteria for a given CFT to have a bulk description. Okay, so the plan for the talk is that after some quick background, I'll give you this proof of MMI using this bit-sket description, which I'll review momentarily. And, well, depending on time, what are the various generalizations and so forth. Okay, so let's start with the background. So Tadashi very nicely reviewed the prescription that he and Ryu had formulated for static configuration, was that the entanglement entropy of a spatial region of a CFT is given by the area of the minimal surface, which is in the bulk, which is anchored on the boundary of this region and homologous to that region. Okay, and you can generalize that. We have generalized that very soon to the covariant prescription that holds for any time-dependent geometry. And in fact, just reminiscing, that idea was given birth to when the three of us met in India at a workshop more than 10 years ago. So, but I won't really use the covariant description in most of the talk. I'll just consider static configuration where we can just use minimal surfaces. So the setup for geometrizing these entanglement relations is you take ADS, so now just for concreteness, I'll be drawing pictures that would correspond to a spatial slice of ADS3, so this is the Poincare disk, and I'll consider the partitions of the subsystems A, B, and C as some spatial regions like this, just simply connected intervals that are adjoining. And one can then construct the minimal surfaces corresponding to each of those. I'll call D to be just the purifier of these three partitions. And you can also construct the minimal surfaces for the union of A and B and union of B and C. And then, well, one thing to note before sort of diving into these relations is that, of course, any one of these entanglement entropies is divergent. It is the same UV divergence, but from the CFT standpoint, there's a UV divergence coming from the modes that are just across the entangling surface, so that's an area law type divergence. From the bulk standpoint, it just corresponds to, again, the same area law by the surface having infinite proper volume as you get to the boundary of the spacetime. Okay, so entanglement entropies are UV divergent, but the mutual information for disjoint regions, say for A and C or B and D, is finite because this UV divergence is coming from the edges cancel out. In fact, if you have an adjoint region, that monogamy of the mutual information between A and B is infinite because there's this extra UV divergence compared to the AB component. But that is cured if you take the conditional mutual information and conditioned on the interval that's in between them. But if you don't condition on the interval that's between them, but some other one, then that quantity can still be infinite. But this tripartite information, whose negativity gives us MMI, is actually finite for all situations. Okay, so you don't have to worry about the entanglement entropies being infinite because we're constructing a well-defined regulator-independent finite quantities when we're talking about this. Yeah?
So this tripartite information or the MMI, it's UV finite, but is it necessarily universal? I mean, the leading piece of this quantity, MMI or tripartite information, does it have any universal pieces? For example, in entanglement entropy, for certain theories, we see universal pieces like logs.
Yes, and in fact, for say topological entanglement, it's the same universal piece. So the MMI, the tripartite information is given by that finite piece.
Nice. Thank you.
So it's very nice to read up because the entanglement entropy has these divergent pieces, but the finite one is retained in this quantity. Thank you. Okay. So let's see how we prove these things. So for example, strong subadditivity just comes from comparing the sort of areas of these surfaces. So if you take AB, that's given by the area of this surface, BC is given by the area of this surface, and then B and ABC areas of these surfaces. So now you can describe the areas on the left-hand side as the area of this surface plus that surface. You just split the surfaces up. And then because this green surface, the minimal surface for region B, is the minimal surface anchored on the region, boundary of the region B, this has to have larger area or cannot have smaller area than this one, and similarly for this, and so the right-hand side is necessarily smaller, okay? So similarly, if you do monogamy of mutual information, the proof is actually the same. Here, the only question is this combined AC system. Well, what it is depends on whether there's any correlation between them or not, or rather, well, whether this set of surfaces has smaller area than this set of surfaces. So in the first case, this would be, the areas of these two would be calculating S of AC, and then these three surfaces cancel, and what you're left with is precisely SSA. In the other alternative, when you have to enlarge these regions so that there is some non-zero correlation, then S of AC is given by area of this, and then these three surfaces cancel. And in fact, you have the same type of proof where you just compare this surface to these surfaces. Okay? So again, it reduces to the same proof as the SSA. So it's identical, and in fact, you can generalize this to the time-dependent case, and in that case also, there is no distinction between the proofs for SSA and MMI. All right, so that's the story for the Ryota-Kanagi and the HRT descriptions. So let's now go on to a different description, calculating the entanglement entropy due to Friedman and Hedrick a few years ago. And maybe Matt Hedrick might review that next week, I'm not sure. So you can reformulate the entanglement entropy in terms of a sort of flux of a vector field or flow lines. A flow, this vector field, a vector field is a flow if it satisfies, if it's divergence free and of bounded norm. And then you can think of the integral curves of this vector field as what Mike and Matt called bit threads. Okay, so pictorially, this is our region, this is the boundary, this is some region A on the boundary, this is the bulk, and the vector field has these integral curves. And the entanglement entropy is calculated by the flux of this vector field V over the region A when you have maximized the flux, when you have fitted as many of these threads as you can subject to this bounded norm condition. Okay, so you can think of this as the threads not ending anywhere in the bulk, and this is them having some finite thickness, quarter of the Planck area type thickness. Okay, so you can also then define a maximizer flow, which I'll denote by V sub A, maximizer flow for a given region A, as any flow that saturates this bound. Okay, so there are infinitely many flows. The only constraint that you have on a maximizer flow is that it has to really saturate this norm bound at the bottleneck, which is the minimal surface of this region A. And so you can very easily see that this is equivalent to sort of the RT prescription, because the bottleneck of the flow, you fit as many threads as you can emerging from this region. The bottleneck is the thing that's most constraining, and then the number of these quarter Planck size threads going through that counts precisely the area of this minimal surface. But we have shown this using sort of the toolkit of Lagrangian duality and convex relaxation last year with Matt. Okay. They have already formulated that, explained that in the original work. So this bit thread picture is a very nice sort of reformulation of the entanglement, holographic entanglement entropy prescription. And in many regards, it sort of behaves much more naturally. So for example, if you had a flow for, if you look how the minimal surface varies as you vary the region, size, or shape, it can actually jump discontinuously in the bulk, whereas the flow itself can behave continuously. It's just the bottleneck would jump. It's also sort of computationally more efficient if you utilize the toolkit of this program. It ties much better to sort of the quantum information theoretic quantities. And so it provides much more intuition. And in fact, it's very, these threads that I mentioned capturing as the sort of the monogamy of entanglement, well, they might be, you might interpret these as sort of those threads subject to the realization that the thread configuration that we're talking about here is predicated not just on the quantum state of the system, but on the specification of a given region. You change the region, you have to change the vector flow. Now, so just to quickly review from the Friedman and Henrich's paper, a bit of this intuition that the threads give us. A useful sort of a lemma or observation is that if you have a maximizer flow for some region, you can use that same maximizer flow, but there exists a maximizer flow for a given region that's simultaneously a maximizer flow for some nested region, some entirely smaller or entirely larger region. Okay, and so, for example, you can find a common maximizer flow on a joint system of A and B, which additionally is also a maximizer flow on any of the subsystems, either A or B, but not generically not both. And so then you can specify these various entanglement quantities in terms of the threads. So for example, conditional entropy would be sort of the given by a number of threads that if you sort of maximize on region B would be left on A. The mutual information is the number, the sort of the correlation between the classical correlation between the systems A and B is given by sort of how many threads you can flip between A and B if you maximize on the A system. And the quantum part of it, the conditional mutual, the quantum bits of the mutual information is given by the bits that connect really the two regions. Okay, so from this sort of description, you can then prove strong subadditivity basically in one line or few lines, but which I'm skipping here, so this is really one line. So you can re-express, the strong subadditivity was positivity of conditional mutual information. You can re-express the conditional mutual information in terms of the sort of previous type of intuition as the maximum flux from the region A after you maximize on C and the common set ABC, whereas the minus set of the minimum such flux. And so because it's a difference of maximum and minimum of the same quantity, then it must be a non-negative number. Similarly, you can think of it, or alternately, you can think of it as sort of the number of threads that are movable between these two regions once you maximize on this. So it's a manifestly positive quantity, but as these folks claim, it's, or observed, it's not, you can't use the same types of tricks for showing MMI. And so one needs some additional ingredient to just postulating this bit thread picture, they thought. Okay, so now I'll show you how that it actually does work. Okay, so here comes the actual proof. Yeah, Rajesh.
It's supposed to capture the quantum entanglement part of the entanglement entropy. Is that the?
It's supposed to capture both. It's supposed to capture all. So for example, the mutual information has a part that is sort of the classical and the quantum amount of correlations.
But in this,
it counts the entanglement entropy, and the entanglement entropy
has both, of course. But in this domain, in this regime, where you have a holographic description, the quantum entanglement dominates over the classical ones. So that's the
interpretation or answer analysis of the fact that MMI is satisfied.
Yeah,
that's the emerging intuition. A priori, that might not have been, that's not obvious yet from the description by the threads.
I mean, so this is this thread picture is for the Ryu-Takanagi for the area law. But when you go beyond the area law with all the higher derivative corrections, can you extend that bit thread picture?
Well, okay, so people are working on that. If you go, so for subleading, well, it's believed that if you take n to be finite, if you really take quantum corrections, MMI need not be satisfied. And
just stringy corrections, let's say.
Okay, stringy, if you're at large n, then this is, MMI should hold for any such holographic dual with higher curvature gravity. And I think people, so the prescription of the threads is not completely, well, okay, is work in progress by Matt. And,
okay. So, but it. Okay.
So I'm not sure how much you can extend what I'll tell you to that situation, though I suspect that once that one is sort of understood, you will be able to extend what I'm saying. But this is speculation. So far, we don't really.
I mean, the reason I was asking was that you said this thread, bit thread picture captures that intuition of monogamy. So is it that it only when there is this monogamy do you expect the bit thread picture to hold, or is it something you expect to hold more generally?
Well, certainly, okay, Matt expects, I think, it to hold more generally. The monogamy picture was something that I just speculated. That's not something that they embraced or proposed. So, but, so I think it is going to hold more generally, although I would, but one might be able to explain that from this, using this intuition. Okay, so how does one show MMI using the threads? So first, the observation that under the assumption of a certain set of flows, so-called cooperative flows, MMI follows very easily. So let's see how that works. So take MMI and rewrite the larger side, the left-hand side, in terms of the bit thread language. So here we have a S of AB is a flux of a maximizer flow for that region AB over AB, and similarly for the other two. And because these are maximizer flows, they're in particular larger than some arbitrary flows. So here, V1, V2, and V3 just denotes just some arbitrary flows, not necessarily maximizing anything, but satisfying the flow relations, meaning they're divergence free and they have bounded norm. Now you can rewrite this expression as integral over just the region A, the region B, and the region C. So you split this out. And now the trick is to find an expression for each of these VIs such that you would immediately get the smaller side. And this is actually very easy. You just solve, you just plug in what you would need to express this. And so the result is just a combination of maximizer flows for these individual regions, A, B, C, and then the ABC region. Okay, so in particular, if we define, I'm going to use a tilde because I'm not a priori, it's not guaranteed that these will be in fact flows. So if we define these objects, these vector fields, as these linear combinations of maximizer flows for the given region, then that expression we had previously reduces precisely to what you want. Okay, so that would prove MMI, provided we can show that these objects that I'm putting in here are in fact flows, do in fact satisfy, well, the divergencelessness is trivial from linearity, but that they do in fact satisfy the norm bound. You had a question? Okay. Okay. And so Matt called such flows, well, in private conversations, cooperative flows, so that's what I'll call them, and hopefully the motivation for that phrasing will become clear momentarily. Okay, so this is what we're instructed to do. And so the reason that it's not trivial is that we're not guaranteed this norm bound. So if we had only average of 2 flows, if there were only 2 flows here, then taking half of it could never exceed the norm bound of absolute value being 1. But we have 4 things, so divided by 2, that's only guaranteeing that each of these are bounded by 2 rather than by 1. Okay, so that's not good enough. And so we need to show that, well, we need somehow to cancel off many of these ingredients so that we're guaranteed to, well, we're able to show that you can bring down this, you're guaranteed to have these bounded by 1 rather than by 2. Okay, so now, most naively, you would want to say, well, let's take these maximizer flows and just cancel them, choose them so that you can cancel them against each other. That's not quite possible. So for example, generically, you can't have VA and VB be same flow because even if you have stuff coming, the threads coming out of A and then threads coming out of B, you're not guaranteed that the bottleneck for the AB system is no smaller than the bottleneck for the individual A system and B system. In fact, it's only equal to it if subadditivity is saturated. Otherwise, it's not true. You can't have a simultaneous flow like that. Now, you can use this nesting lemma that if you have a maximizer on ABC, you can set that to be the same as one of these, but only one of these. Okay? Now, in fact, if there is no correlation, let's say, between A and C, you're in better shape. So in fact, you can find a simultaneous maximizer flow for both A and C. And so then you can show the norm bound is satisfied because, well, if you additionally choose the maximizer flow for B to be the same as that of for ABC, then all of these 3 quantities, in fact, are described by something that is already a flow by construction. So that's great, except that you're not always guaranteed that this will be the case. And in fact, if it's not the case, then, well, so what can we do? So you can't set VA to be VC, but you still need some bit of threads to go between A and C. So at best, you can choose VA to be minus VC. You can apply the nesting for the, say, C to be nested within BCD, and then the flow for the BCD region is minus the flow for the A region. Okay, so that you can do, but that doesn't help because then these 2 are in fact still exceeding the norm bound. Okay, so we have to find something. We have to work harder. Okay, so, yeah. Mm-hmm.
Mod V1 equals to 1, mod V2 equals to mod, and mod V3 are less than 1. Doesn't that uniquely fix like what?
No, because the only constraint, well, first of all, maximizer flow is not uniquely fixed to start with. It's only fixed on the minimal surface, on the bottleneck. Elsewhere, the flow can be completely floppy.
I'm saying that in that relation that V1, V2, V3, if you just took like arbitrary coefficients on the right, combining the different maximizer flows, and you just take the condition that mod V is less than 1 for all of them, doesn't that, it should give you some condition as to what those coefficients should be, right? Means.
Oh, the expressions.
I'm saying instead of taking half in the
coefficients in these expressions.
Yeah.
So that is uniquely fixed by saying you want to relate the left-hand side to the right-hand side. That's indeed true.
Yeah. Okay.
So you can, I mean, it's sort of back of the envelope calculation to check that. Easier to check if you have these expressions to plug it back in that it gives you the other one. But it's just a system of 3 linear equations.
Thank you.
Any question?
Actually, I had a question. So if I understood, if I'm following this right, so if you put a 1/4 in all of them, then you'll be okay.
You'll be fine, yeah.
But then you'll prove something like LHS is greater than or equal to half of RHS. So it's a weaker thing than what you want to prove.
Priori, yes.
Okay. that you have already proved in some sense. I mean, the weaker thing already follows.
The stronger one, so then the weaker one follows automatically. But yes, you know already without any work that the weaker bound is satisfied. Okay, so how can we do this? Okay, so how do we construct flows V1, V2, and V3 that are guaranteed to really be flows to satisfy the norm bound for any set of regions ABC, and so we're instructed to find the maximizer flow for ABC and ABC such that the expressions we had on the previous page, these ones actually do satisfy this norm bound. Okay, so it's not going to be true for any maximizer flows here, but we're going to construct specific maximizer flows that will guarantee that the norm bound is satisfied. So how do we do it? So let's see, how could we do it? So to construct these, we'll try to separate, sort of rewrite a maximizer flow for a given region as being built up of strands of the flow that are sort of defined by which two regions they're connecting. And so in particular, the maximizer flow for VA, you could separate into the strand that goes, well, from A to B, which is denoted by this, and the strand that goes from A to D. And similarly for the other regions. Now, I have sort of, without loss of generality, assumed that the A plus C minimal surface areas are smaller than the B plus D. You don't have to assume that. You can take the B plus D smaller, and then the set of strands that you would use would be the ones that go this way. And so everything would stay the same. In fact, this tripartite information is not just cyclically, well, not just sort of permutation symmetric under ABC, but also symmetric under purification. And so you could substitute, you could take D to be one of your regions and then redefine, you would still get the same MMI. And so you can really sort of think of this as for the simple interval configurations as without loss of generality. In any case, so suppose we do write the maximizer flows in terms of these strands, okay, where the strand, we use the same strands as part of the flow from B to A and from A to B, and similarly with the other ones. Okay, so, and we separate them, so suppose we can separate them into disjoint bulk regions. Okay, that they flow through disjoint bulk regions as I have shown. So if that is the case, so I'll show you that that is indeed the case later, but let's see first the logic. If that is the case, then, well, this is just the description of these maximizer flows decomposed into these individual strands and which of these 5 regions they're activated in. If you do that decomposition, well, then the VIs, you just plug in the expressions that we had, you can check very easily that even though these VIs really are composed of multiple strands, you never activate more than one strand, in the given region, because after all, that's how you decomposed it. And so each of these is guaranteed to be a flow to satisfy the norm bound. Okay? So so now this explains this title or this label, cooperative flows. These flows would be cooperating with each other, that they wouldn't interfere with each other, they wouldn't intersect. Okay? So why is it, how are we guaranteed that there exists such a separation, that we can construct, in fact, strands that do not interfere with each other? Oh, yeah.
Just from the picture.
So from the picture and in actuality, there's plenty of bulk regions that are not going to be activated.
I see. So is there any significance to these paths?
The significance is that, the other option doesn't happen, that you would not be able to fit the necessary flows in. The fact that there is more space is that there's still a lot of freedom in how you choose these strands. So they can be weaving around. Again, the only place that they're really constrained is these minimal surfaces. So in some sense, you can think of it as the bulk, being asymptotically ADS and getting large, therefore near the boundary. If you had some other geometry that didn't have this asymptopia, then you might be filling the bulk, but that would be very artificial. You wouldn't get the usual ADS CFT type correspondence.
Thank you.
Or like that?
Well, so I don't have to activate it because, okay, I'll actually show that on one of the, either next slide or the one after that. But I'm not ignoring it. I'll argue that you don't need it.
No, but you can remove B and start a flow from A to C so that there will be no intersecting.
Yeah. So, but you cannot do it if the area of these two surfaces is larger than the area of these two surfaces, because then you would not fit all the strands that come out of A, let's say, would not be able to fit only into these two regions. Well, sorry, I said it, sorry, I apologize, I said it the wrong way. If all the strands from B, okay, which if you ignore the BD flow and instead had the AC flow, the strands from B, if these two areas are larger than these two, would not be able to be maximally dense on these two surfaces because they would have nowhere to go. And either they would have to violate the norm bound or they would have to violate the divergence free bound. But if it happens that the areas of A and C are larger than the B and D, then you would have the opposite situations of having strands this way, but not needing the strands this way. So one or the other set of, you're just comparing pairs of areas, so one is larger or the other one is larger. And in both cases, if this is larger, it's this strand, and if this is larger, it's the other strand. It's symmetric situation. So I'm going to focus, just to be particular, I'll just focus on the case where the mutual information between A and C is 0, but you can do the same thing with the other case.
So when you're saying that these lines will not interfere with each other, so will there be like a fixed point in that region where the lines are, yeah. Is there?
Well, no, because again, as I said, these flows are pretty floppy outside of these minimal surfaces. So I could have taken, so this is just a schematic picture. So I can have enlarged the region A to be filling up this, and then I could have taken the strands, as long as they cross these two surfaces, the A surface and the B surface for the A to B flow, as long as they cross that perpendicularly, they could then deviate and flop around in here. So it can be a fixed point once you specify a unique, well, once you specify a specific flow configuration, but there is nothing special about specifying a unique flow configuration because you can specify infinitely many others. So that means that I don't think there is any significance to any one of those fixed points. Right, so why is it always possible to choose these strands? So you can figure out what are the constraints on these strands, and the constraints are that they have to match, that they have to have the same areas. Let's see, did I have a picture? No, I didn't. Let me, now that I have flashed these whole bunch of messy looking equations, let me go back to the picture and explain what those equations are saying. Okay, so if you have a same strand you're using for the A to B and B to A, well then the area which they cover on this surface has to be the same as the area on this surface, and similarly for all the other pairs. Okay, so that's one set of equations. The other set of equations was that, say, the ones that pass from A, that decompose into A to B and A to D, they have to add up to that full area of A, which it doesn't look like in this picture, but that's the condition for this decomposition, because they're maximizer flows, which means that they have to saturate the norm bound everywhere on that minimal surface. I see I'm out of time, so let me speed up. There will be an alarm clock in 20 seconds. Okay, so that's the constraint on the areas, but it gives you only 9 equations for 10 unknowns, and in fact there's therefore one parameter family of solutions which you can see geometrically how you would construct it, so you have a full freedom of how you would construct this. So that's always possible. And then the other thing to show is that once you have fitted these strands through the minimal surfaces, that they don't interfere with each other elsewhere. That you can show by combing the strands sort of to be maximally compact, saturating the norm bound not just on the minimal surface but away from it, by using foliations by minimal surfaces. And this is where the bulk locality comes into it. So, well, okay, sorry. Let me just go back to this picture. So here, once you show that, say, for example, these two strands don't interfere with each other on the minimal surface, I can comb them by foliating, say, this region with surfaces, with minimal surfaces that sort of look like this, and comb this B flow by foliating with surfaces that have different endpoints, such that you can show that once they get through this surface, which is perpendicular, they have to start bending away from each other. Okay, and this argument is very robust to deforming, the space-time geometry and therefore the state, to deforming the regions, to having some more complicated topology, all such things. It just rests on taking minimal surfaces to guide where these strands are, and those things are guaranteed to not intersect with each other if they're anchored on nested regions. So I can, if someone's interested, I can explain that later. Let me just sort of very quickly wrap. You can generalize this construction to sort of having arbitrary regions with various geometries. You should be able to generalize it to higher dimensions, because after all, there you don't even have to, you can have both simultaneous flow between, say, A and C and B and D, because the strands can pass around each other in the extra direction. Similarly, one should be able to do this more easily when you have a sort of a time-dependent, when you utilize the freedom of these threads to meander in time. They're only constrained to pass through the extremal surface, but they can be floppy, not just in space, but in time elsewhere. And, well, there's a nice story about, well, it's an interesting question, what happens if you take not MMI, but these other, well, inequalities that are based on higher number of partitions. So, for example, there's a analogous inequality that uses 5 regions, 5 partitions, the so-called 5-region cyclic inequality, and you can sort of try to play the same game. You can construct what should be flows from, maximizer flows from these various regions. Here it's much more subtle, and it's not that what the proof that I sketched previously doesn't really, you have to work harder, because now you can't have a simultaneous maximizer flow, say, through this surface and through this surface, because they intersect each other, so you can't have a same vector field being perpendicular to both of them at these intersection points. But, so again, I can tell you a bit more about how this might work afterwards. But let me just conclude. Okay, so for MMI, we have demonstrated the proof is complete. These cooperative flows are guaranteed to exist, and that the thing that guaranteed it was, in a sense, the bulk locality. And so you can always comb these strands into cooperative flows. And so this is the sort of feature that distinguishes the proof of SSA from MMI, which again, it rests much more crucially on bulk locality. Okay, and then you can sort of have various of these generalizations and so forth, and try to understand how you would, for example, invert the method to think of other entanglement relations, whether you could sort of use it for other measures of entanglement, how it relates to, say, entanglement of purification, and so forth. So let me stop here.
Yeah, so one very quick thing, the norm bound that you have, I mean, you essentially require that bound to be, like that C to be strictly greater than 0, right? It cannot vanish.
The norm of the V?
The norm of the V, right.
Oh, it can vanish where the strands are not present. So let's see. So let me say go to one of these pictures. So the flows that we constructed would have a norm bound 0. If this was related strands, they would have, the vector field would only be present, for this guy would only be present in this region and 0. That vector would be 0 everywhere. Right. So that's where the norm is 0.
So in this case, the entire analysis would work just by saying that you have a positive norm vector field. Is that true?
Well,
I mean, you just need.
You don't need to have a non-vanishing norm vector field. You just have to have a bound from above. It can't get more than norm.
Would the argument of the max flow min cut theorem work if you have? I'm asking. I mean, I don't.
Well, it's the only constraint is because it's a maximizer flow. It has to be saturating that norm bound on the given minimal surface. Okay, so there it has to be equal to 1. But else, it can ever be larger than 1 anywhere, but it can be smaller, generically is smaller than 1 elsewhere, and it can go to 0 without a problem. It just has to be 1 on the minimal surface, and then by continuing it can't vanish too quickly off of it. But yeah, it becomes more and more floppy, and you're free to describe where those threads go as you go towards the boundary, where after all, you have infinite area. If you took this surface and took it to like closer and closer to the boundary, it would have, that area would go to infinity. Well, sorry, even if you regulate it of these ends. But if this part went to the boundary, its area would increase, which means that the same strands would now fit through with much smaller density. And therefore, in this discretized picture, there would be plenty of room in between on these other surfaces.
I see. Thank you.
Yeah, hi. Maybe you already said this, but if you look at the A and C regions, right? So if you start with that point there, these threads bend this way, right? I mean, they bend this way, and the other ones, in the C region, or in the E region, sorry, they bend this way. Is this, so presumably there's a thread that goes straight in, right? Is there some significance to that, or?
Oh, so you can, okay, so the construction for these, when I had these 9 equations with 10 unknowns, one way you could sort of see the one parameter family of solutions is take say this surface and pick some point on it, which will be the separator between the A strand and the E strand. Now that point has a lot of freedom, okay, so there won't be any distinction there. So once you pick a point somewhere on the surface, then that determines the corresponding point on this surface and on this surface. And then you have a freedom, you have a one parameter freedom, okay, between choosing where you have to make this separation, which would determine these two separations, such that these two remaining pieces are the same area. So there is no significance to the partition.
Sorry, this is a very quick question. So it seems like the picture of the bit thread is probably related to calibration forms of calibrated submanifolds. Is that Is that a useful way to think about it, or?
Might be, but save that question for next week where Matt will be here because.
Oh, okay.
So is flows which don't satisfy this cooperative property, is it possible to have some gravity dual description?
I would say no.
Classical gravity guarantees this property. That's what you explain.
Yes.
But there are some exotic gravity or some quantum correction to gravity. Do they have some physical meaning? Do you expect, or?
Well, quantum correction is going to be different because then this prescription doesn't apply. The flows don't have to satisfy this divergence.
I see. Yes.
But in terms of just higher curvature corrections, basically, so the thing that the cooperation really rests on is that, so if you have, so how can one comb flows? First of all, you can pick a set of minimal surfaces. Let's pick a simple set of minimal surfaces that are anchored on nested regions. So there's a small region, larger region, larger region, and so forth. And if you pick this like that, the normal to these surfaces, because these are minimal surfaces, they have zero expansion, and so then the normals to it don't change the area. So if you fix the density to satisfy the norm bound here, it's going to keep satisfying it. And so these sort of guide the flow. Okay, so these would describe the strands. These are just generating the strands that are guaranteed to be maximally dense, maximally collimated, not just on a given extremal minimal surface, but elsewhere from it as well. So now, if you had so what is the existence guaranteed by? It's guaranteed by not having a situation where you would have a minimal surface, say, anchored on this region, intersect a minimal surface that would be anchored on a larger region, let's say, doing something like this. And that's guaranteed because if these were both minimal surfaces, then of course you could find a smaller area surface by sort of rounding off one of the corners. So the foliation, the nesting for the foliation, at least for the static case, is guaranteed manifestly. For the time dependence case, it's guaranteed by nesting of the entanglement wedges, which is also in the which we've also shown. So it's guaranteed fully, and that's the thing that allows us to guide these flows away from each other. Okay, so to not satisfy that, you would have to to come up with a bulk geometry that doesn't have the property that you could sort of say round off the corner and decrease the area, but that just follows universally for any sort of metric you have, independently of the dynamics.
Okay, if there are no further questions, let's thank Veronika again.